afternoon session. I've been asked to make a couple of announcements. One of which is refrain from plugging in laptops into wall sockets because they could trip people. The other is please be sure and turn off your cell phones. Otherwise, bad things might happen. This afternoon, our first speaker is Michael Jordan from Berkeley, and he's going to talk about kernel-based contrast functions for sufficient dimension reduction.
All right, the last time I was at the Newton Institute was about 10 years ago. Mike Titterington invited me to a conference on graphical models. So I gave a very Bayesian talk. And just to show that I'm bilingual, I'm giving a very non-Bayesian talk today. So this talk luckily follows Dennis Cook's lovely presentation earlier. So if everyone attended that, I hope you did. You now know what sufficient dimension reduction is. I don't have to repeat that. I will give a little bit of overview in case someone didn't attend. But I think that it is nice to set, there are several themes in the workshop, I guess, this week, but it's nice to contrast this with what you've been hearing earlier in the week. So nothing is sparse really here, at least in the original set of variables. So sufficient dimension reduction is about finding a subspace which best represents a regression or a classification. So if I take my original variables and I rotate them in some way, then all the original variables are relevant. But there might be a small dimensional subspace which is relevant for the, so we might be sparse in some subspace, but we're certainly not sparse in the original variables. And there are problems for which one or the other is the right way to think, but these are certainly somewhat distinct ways of thinking. On the other hand, methodologically, there are lots of relationships to be drawn between these, and I think that's one of the interesting themes of the workshop. Another theme of the workshop is manifold learning, quote unquote. Where you are simply trying to find something about, learn something about the manifold underlying the data, irrespective of any response. So I'm going to try to bring that theme in as well into this talk, where we're going to do sufficient dimension reduction on manifolds. Let me acknowledge a couple of collaborators. A couple more will come up later, but Kenji Fukumizu and Institute of Statistical Mathematics in Japan and Francis Bach in France have been collaborators throughout this work. So I'll remind you briefly what dimension reduction is in this regression setting, and particularly emphasize conditional independence as kind of the road into this set of ideas. And then we're going to talk about my preferred technique for assessing conditional independence and leading to an algorithm for doing dimension reduction, and this is going to be to use operators on reproducing kernel Hilbert spaces. So you may have heard other talks where people use reproducing kernel Hilbert spaces as sources of basis functions, basis expansions for regression or classification. This will be a slightly different use of the set of ideas. We're interested in the operators on the Hilbert space, not the entities in the Hilbert space per se. So then I'll discuss this methodology, and the first half of the talk will be about finding subspaces, so the classical setting of sufficient dimension reduction, and then we'll talk about a somewhat exotic idea, which is to use the same set of ideas to find manifolds, or to explore manifolds. Okay, so to remind you a little bit about what was in the previous talk, we are in the regression setting here, and I mean regression very generally. It could include generalized linear modeling or classification sorts of models and so on. But critically, we observe x-y pairs, and x is going to be high dimensional, and y is not going to necessarily be unidimensional. It'll be multidimensional in general here, but generally lower dimension than x. And the goal is to find, at least in the first part of the talk, a subspace, so a linear manifold of the covariate space that in some sense retains the information pertinent to the response y. And this has been a somewhat small specialized literature in a sense. There's probably about a dozen people who have contributed to it over a couple of decades. And I think one of the interesting aspects of it has been there's been a semi-parametric formulation of it. So the conditional distribution P of y given x is treated as a nuisance parameter in essence, so it's treated non-parametrically, and what we'd like to find is the parameter S, i.e. the subspace, and that parameter can be either thought of as a Stiefel manifold or a Grassmann manifold, but it's in some sense the subspace itself, which is the parametric part that's of interest. And we want to not care about the P of y given x. So it's kind of an odd setting for regression, but it's just like in linear discriminant analysis. You this is sort of a pre-processing stage. You find the subspace, and then you start over again. Having found the subspace, then you're free to do any kind of regression or classification methodology on that subspace you want. Okay, so now, somewhat more philosophically, let's think about regression more generally. You know, so from Fisher and others, we were sort of told that we shouldn't be thinking about the covariate x very much. It's ancillary for the parameter, any parameters in P of y given x, so let's not even worry about it at all. And that doesn't really give you much of a good starting place if you're interested in doing something about x. So the SDR literature has aimed at making use in some sense of the randomness in x. Now, of course, there's situations like experimental design where it's not really clear that there's much randomness in x per se, and so you have to kind of worry about whether the techniques are applicable in those situations. But let's think more broadly about situations where x really is random. You'd like to somehow make use of that to help identify subspaces in x, still taking into account y. Starting with Kerchow Lee and others, inverse regression has been the main technology for doing that. Inverse regression simply goes from y back to x, and under various sorts of assumptions, some of which are fairly strong, for example, ellipticity of the distribution of x, then the forward and inverse regressions give you the same answer. Okay, so inverse regression, if y is univariate, then the inverse regression is just a path, but it lies in the same subspace that the forward regression lies in. So if you somehow can find that path, and then find the subspace that's spanned by that path is spanned by, you've done the job you want to do in the forward direction. Okay, so that's been the main technique. So this talk is going to be a little bit unusual in that it is going to aim at using the randomness in x. We're going to treat it as a random variable, but we're not going to use inverse regression. Okay, so a little bit more on at least a kind of not too formal of a setup here. So we have y and x. I apologize for using m instead of p. Just somewhat informally, let's define an EDR, an effective direction for regression, as a projection given by a matrix B such that the conditional distribution of y given x is the same after you project onto the subspace spanned by the columns of B. Now, there are many existing methods that aim in one way or another to find this matrix B or find the manifold that it lies in. And so here's a list of some of them. And most of them make strong assumptions. Sir was the first one about 1991. It assumed ellipticity of the distribution of x. And as time has gone on, people have tried to move it further and further away from strong assumptions. But still, I think the literature has not gone as far as one would want it to go. And so I'm going to attempt to go about as far as I think you can go in this talk in removing assumptions on x. Okay, so here's just a little trivial example. Here's a regression, a nonlinear regression given by a logistic regression. So x1 is the EDR direction. We'd like to ignore x2 and project onto x1, and we'll see this marginal. If we projected it mistakenly onto x2, we would see this. And you sort of look at if you look at the x1, x2 scatter of this, if you project down, you can sort of see there's not a lot of information. And in particular principal components here, it's not really clear it's the best guide for finding x1. I could certainly change the variance in the x2, make it larger in the x2 direction, and mask the fact that x1 is the EDR direction. So it seems like it's a really practical problem here to find x1, and of course that leads you to think about variable selection kind of methodology that you've heard about yesterday. But if we just simply rotate this, we'd like to find some linear combination of x1 and x2. That's a slightly different character problem. So I think one of the most useful pieces of thought that went into the SDR literature is the recognition that this is closely related to conditional independence. So let's take B transpose X and complete the matrix B with a matrix C whose columns are orthogonal to B. And so we can now represent X as a pair UV projecting onto complementary subspaces B via B and C. Okay, so if B gives the projector onto this effective dimension reduction subspace, that's equivalent to saying that the conditional distribution of y given x is equal to the conditional distribution of y given this projection. And that's equivalent to expanding x into u and v. this equality here for all y, u, and v, and that's simply a statement of conditional independence. Okay, so graphically we can represent it this way. All right, so it's a very simple sequence of arguments, but it leads you to a principle, which is that if you want to find these EDR spaces, what you'd really like to do is characterize conditional independence, and in particular characterize departures from conditional independence, and then optimize that characterization. So get yourself some sort of a contrast function via characterizing conditional independence. So that's not what's typically been done in the literature. The literature is mainly focused on methodology that's usually clever, intuitively motivated, like sliced inverse regression, and then showing that it works in some sense, okay? But we're going to sort of go at this a little bit more foundationally. We're going to characterize conditional independence and then get a method from doing that. Okay, so let's talk about how we're going to do that. Okay, so if you've ever heard a Grace-Wabba talk, you know what a reproducing Hilbert space is. Basically, it's a Hilbert space that's a small Hilbert space in some sense. So it's got smooth functions in it. And instead of L2, which is a really big Hilbert space where you can't compute anything with practical amounts of time, and this is a small Hilbert space where you can do computations that can be polynomial time. So that's really the main reason that they've become so widely used, I think. On the other hand, it's a small Hilbert space, and the functions in it are very smooth, and so you can debate whether they're appropriate for lots of problems in regression classification, where things like maybe Besov might be more appropriate. But I think you're going to see a different application of the ideas here, where I think it's actually not, it's more appropriate. So one perspective then is it's a small Hilbert space of smooth functions. The other perspective is that it allows you to do what is often called kernelization, which is that you, by picking a kernel, you map data into a kernel, into a reproducing kernel Hilbert space, and inner products in that space are given by evaluations of a kernel in the original space. So that's called kernelization. And again, if you were to look at L2, inner products there can be hard to compute realistically, whereas here they're easy to compute. You just evaluate your kernel function. And I found this most attractive when I was taught by people like David Hausler and others, that there are lots of kernels, for example, string matching. If I take two strings, which can be of arbitrary lengths, and do a dynamic program to align them to each other, and then do that over a set of n strings, I get an n by n matrix, which is positive definite, so I've defined a kernel. So therefore, I can start with a non-Euclidean set of data, or data which are not in a Euclidean space of any kind, define a kernel on them, say by dynamic programming, and I've now effectively defined a Hilbert space in which I can do all the statistical kind of things I'd like to do, like discriminant analysis or whatever. So I think that's the second reason why these methods have become so widely used. All right, but there's a third reason, which is the purpose of this talk. We're going to use RKSHs to characterize conditional independence. So this line of thinking came out of work that I did with my student Francis Bach several years ago, thinking about canonical correlation and how to use canonical correlation in Hilbert spaces as a way to characterize independence. All right, so we did that, and that led to a methodology for independent component analysis. But that wasn't enough, so this SDR problem is not just about independence, it's about conditional independence. So the next step then was to figure out how to use things like canonical correlation for characterizing conditional independence. So the basic idea is going to be, though, the spirit is that of canonical correlation. So I'm going to take a random variable x, and I'm going to transform that into phi of x, which is going to be a vector in some reproducing kernel Hilbert space. So that's going to be a random variable. And then I'm going to do the same thing for the response y. So I'm going to have a reproducing kernel Hilbert space for y. I'm going to have one for x. And then in some sense, I'm going to capture dependence between these random variables, phi of x and phi of y, maybe using something like canonical correlation, second order statistics. And if these spaces are rich enough, that's going to characterize independence among the x's and y's, even though I'm using simple second order methods in the RKSH. Okay, so let's write down a few more definitions. So a positive definite kernel is just a function from omega across omega to the reals. It's positive definite if, when you evaluate it on any subset of n points, you get a Gram matrix, which is positive semi-definite as a matrix. So that's one of many characterizations. And so in particular, the Gaussian RBF kernel is a positive definite function It's not obvious that it is just looking at its form, but it is. And so given a positive definite function, you can define a reproducible Hilbert space. The classical theory tells us if you have a positive definite kernel, then there exists a Hilbert space such that when you evaluate the kernel at a fixed point x in its second argument, and this is now a function of the first argument, that's a function that lives in the Hilbert space. And the span of all of those kernel evaluations for all x is dense in the Hilbert space. And then moreover, the most important property is the reproducing property, which is you take the inner product in that Hilbert space of this function, which does live in the space by point 1, with any function that lives in the space, you would simply evaluate f at x. And if you haven't seen RKSs before, it's nice to compare this to L2, where if this were the delta function, the Dirac delta, then the Dirac delta inner product with f gives me f of x. And so this is just the generalization of that. But of course, the problem there is that the Dirac delta does not live in L2. Okay, so it's too rich of a class of functions for you to be able to get evaluation just by inner products. But in these smaller Hilbert spaces, you get evaluation by inner products with a simple convolution. That's the reproducing property. Okay, so basically this turns into a kind of a functional data analysis sort of problem. Instead of working with data points x, I map them into functions in a Hilbert space given by k dot comma x. So that's a function in the Hilbert space. And so I've used the notation phi of x is just this function, the image of x in the Hilbert space. So data went over into functional objects phi. And so, as I pointed out computationally, why do you use these things? Well, because now inner products become easy to evaluate. So if I evaluate the inner product between the image of x and y, it just becomes a kernel evaluation. And that can be evaluated just by plugging in f is it lives in the Hilbert space, so it's some expansion. And g similarly is some expansion. These things are dense. And therefore, the inner product, just by expanding out, becomes simply this evaluation on points xi and xj. All right, so the key point is that the computational cost basically depends on the sample size. So if you're doing non-parametrics, you're sort of prepared to pay cost, and it depends on the sample size. It doesn't depend on the dimensionality of the space that the data live in. So that's the main advantageous aspect of these things for high-dimensional data when you have relatively small sample size. And the algorithms often turn out to be n cubed, so sample size can't grow too quickly. But if you're smarter, you can get these down to below n cubed with numerical tricks. Okay, so that's the kind of basic layout of an RKSH. Now let's talk about operators on the RKSH. Okay, so x and y are random variables on omega x and omega y. We put RKSHs on those spaces, and now we define random variables in the RKSH. We induce random variables in the RKSH. And we can now define a covariance matrix, sigma sub yx, just defined as follows. Covariance between a image of y and the inner product of x with an argument. So this is going to be an operator on the xh sub x space, and its image is going to be in the x sub y space. So on the next slide, I make that more clear. So the real way to understand what this object is, it's an operator from hx to xy, and it behaves in a way you would hope it to behave. It looks like covariance. So if I want to get the covariance between f of x and g of y for arbitrary functions f and g that live in my Hilbert space, I can get that by taking this bilinear form here, g, this operator f, and get the covariance. So there's a theorem that says that this operator does exist, and its evaluation in this bilinear sense leads to this covariance. All right, so in the Euclidean case, this is what you would sort of hope to have achieved as a generalization, because in the Euclidean case, the covariance matrix just has this form, and if you view it as a matrix operator, you simply get the covariance between the projections of y on the b and a onto x. So this looks like canonical correlation, and you would therefore expect that these kind of operators here should be something like a functional canonical correlation. Okay, so let's now talk about just independence, not conditional independence, but independence. So we're going to talk about cross-covariance operators. And so if these reproducing kernel Hilbert spaces are rich enough, and what that means is that they are, the other terminology is probability determining, and you get a probability determining RKSH if your kernel is universal, and A universal kernel is basically one whose leads to an RKSH which is dense in the Banach space of continuous functions with the sup norm. Okay, so that's the definition. So in particular, the Gaussian RBF kernel is well known to be universal in this sense, but there are many others. Okay, so it is a fact that if you have independence between two random variables, then that you have that if and only if the cross covariance operator is equal to the 0 operator. And so this holds just by definition that if this covariance is equal to 0 for all f and g in the reproducing Hilbert space, and expanding it out, you get this. Okay, so obviously in one direction, in this forward direction, this is trivial. And in the opposite direction, it's a theorem, and it depends on the fact that this kernel is rich enough. In essence, this kernel has all the moments that you would need. When you take these expectations, you can get sort of all moments, and if you get equality for all moments, then effectively you've got independence. So another way to see this is that if you just go back to characteristic functions, so we know we have independence if there should have been an equal sign here. There's a missing equal sign in there. If this thing on the left-hand side is equal to these guys on the right. So this is the same thing as on the previous slide, but just using these special functions instead of f and g, we have these special functions. So here we're working basically in L2, because these sinusoids span L2, but L2 is too big of a Hilbert space for us to work with effectively. So it's nice that this same kind of theorem holds in these nice small tractable Hilbert spaces using things like RBF functions and not using these nasty Fourier objects. Okay? So anyway, this theorem that we have is just basically, though, a generalization of the classical use of characteristic functions in L2. Okay, but now let's move on to conditional independence. Okay, so we're now going to define another operator. So we had this sigma yx before, but now let's define a conditional covariance operator. So this operator is, of course, known and defined in the RKSH literature. And we'll define it in the following way, just by analogy with the finite dimensional situation with Gaussians. The fact that we have a sigma xx minus 1 here is really just a notational shorthand. This inverse doesn't necessarily exist, but in our paper we show how to handle this when that inverse does not exist. Okay, so if the kernel is universal, then when you use this guy as a bilinear operator and evaluate it on G, then you can show that this gives you basically the conditional variance of G, and then the expectation is over the X. Okay, so this is again what you'd kind of expect from the simpler finite dimensional Euclidean situation. If I have Gaussians, then this matrix operator here gives me the conditional variance. Okay. All right, so that's what a conditional covariance operator is. It's an operator which generates these conditional covariances. And it has a monotonicity property. So if I take X and I partition it, and then I condition only on a part of X, then I have a larger operator in the sense, in whatever sense you want to define for self-adjoint operators. So either determinants or traces or some other ordering for self-adjoint operators. Okay, so this is starting to look promising. We now have a notion that we're ordering, so we can start to work towards an optimization principle, some sort of a contrast function. Okay, so we have proved a theorem which says the following, that we can now characterize conditional independence with these operators. Define X to be partitioned into UV, and then let Y be a random vector. Put reproducing kernel Hilbert spaces on everything with these kernels. And now it is a fact that you have conditional independence of Y and V given U if and only if these conditional, so this is always bigger than this, but if you have equality, then you get conditional independence. Okay, so with that theorem in hand, we now have a characterization and we have a notion of monotonicity, so we can now write down an optimization principle and get ourselves some kind of a procedure. Okay, so what is that procedure? Yeah.
So in a word, what's the white Gaussian cones? I mean, what's the
what?
So that theorem said in the case of Gaussian cones.
Yes, or universal kernels in general. So universal kernels in general.
All universal.
All universal kernels, that theorem holds, yeah. Okay, so we have this universal kernel, and let's now make our variable u be b transpose x. And in the sense of the partial order, we have this, as we said before, and if we actually achieve equality for some choice of b, we've now managed to find our self-conditional independence. Okay, so that's kind of that is the natural setup for the SDR problem. You know, it captures the basic objective function if you're 0. And now you can ask, let's try to optimize this. So let's take some. We need to implement this notion of the partial order on self-adjoint operators. So let's take the trace as a particular way to do that. We could use others like the determinant, but we've been able to do some theory using the trace, and it's worked well in practice. All right, so we simply want to optimize this operator in the trace norm over the Stiefel manifold, over the set of matrices such that B transpose B is equal to identity. Okay, so that's a well-posed optimization problem, and we can, so one of the things we do in my group is worry about numerical methods for optimizing these sorts of things on Stiefel manifolds, and so we kind of know how to do this and make this into an effective procedure. All right, so now how do we get an estimator? That was kind of the population story. Well, we're just going to plug in kernel evaluations everywhere, and we'll end up getting Gram matrices. So we're going to simply define an empirical version of the cross-covariance operator simply by taking the empirical sum of what we had before. And then this object then will give an empirical covariance, and there's some kind of a glitch here, but if I evaluate this operator on F and G, then I'll simply get the empirical covariance. And so now I can plug that into the conditional covariance operator and define this object here as just the empirical version of what we had before. And now we're going to add a regularization coefficient to this object that we take the inverse of. And it's sort of for obvious reasons. If you know the functional data analysis literature and kind of functional canonical correlation, you'll know that you need to add this. If you don't add it, you sort of get a meaningless quantity. All right, so when we do theory, we'll need to actually say something about this, how this thing goes to 0. Okay, so there's our empirical version of this, and now we're going to simply take the trace of this and optimize that over matrices B. Okay, so we simply write this down, and then we recognize that these matrices are given by kernel evaluations, and so they simply become centered Gram matrices. So we have a centered Gram matrix for the Y variable, one for the U variable. We simply, centered means you simply subtract off the mean. We simply plug those in, and we get this is our final form of the contrast function. So minimize the trace of this thing where these are Gram matrices. They're n by n matrices if you have n data points.
Quick question.
Yes.
What is the operator I here?
What is the operator of I? It's the identity operator.
But does that saying, as a covariance operator, is that saying all functions are independent of each other?
Okay, no, I took the covariance operator to motivate to motivate a form that I want to optimize. But now when I actually go to the numerical optimization, I've got to regularize.
And you need a coordinate system to do that, right?
Well, I'm going to need, my Gram matrices basically are going to define my coordinate system. Once I have n data points, that will define a specific coordinate system. Let me just briefly relate this to some of the existing methods. I've sort of alluded to the fact that these need various kinds of assumptions. So, SIR, does a principal component analysis on sort of histograms of the inverse regression, and you need some form of assumption of the distribution of X, which is pretty strong. Elliptic assumption is typically what's invoked. And the various other methods either make assumptions on the regression itself, for example, that it's additive or that it's linear, or make strong assumptions on the relationship between Y and X. So in this, PhD is, for example, and this is true of several of the other methods, Y must be one-dimensional. So this method doesn't make any assumptions on Y, and you will see the assumptions it makes on X here in a minute when I give a consistency result. The other point to make is that this is quite effective in practice. It's certainly easy to cook up situations where X is non-elliptical. For example, suppose X is given by a mixture model, and you can make SIR fail quite badly, and KDR works there. We did this on a bunch of benchmark data sets, and here's just one of the examples. This is wine data from the UCI Irvine data set. So here we've used a RBF kernel, and this is projection given by onto two components for KDR. And so in this case, linear methods also were reasonably good. In KDR, its nonlinearity, it allowed you to separate out a little bit better. And you can see here that slice inverse regression is not very effective here, and we found that to be true on many of these data sets. Basically, the X variables are not elliptical in many of these situations. Okay, so we do have a theorem on consistency. So this is a hard object to work with. We're being very non-parametric here, and we don't have any distribution theory at this point. But we do have a consistency result, and this took quite a bit of work. So we have a technical report on at the statistics department web server at Berkeley, if you want to see details. But basically underlying this theorem is a fair amount of empirical process theory in Hilbert spaces and in Banach spaces. Under some conditions, which I didn't elaborate here, which I can get into if people are interested, if the kernel is bounded and continuous, and if the regularization parameter goes to 0 at this rate, then we can say that the estimate, and again, I think there's a font issue here, that should be B hat n, so that's the estimator given by this procedure, will fall in the set U, which contains the set of optimal parameters that minimizes trace as n goes to infinity. Okay, so that happens with probability 1. And so basically we do this, we work this, we prove this theorem by proving a uniform convergence result over the Hilbert space for things like the trace of these cross-covariance operators. So you basically go through the same sequence of arguments you usually go through in empirical process theory with symmetrization and tail-bound kind of things and a chaining lemma, and you simply do these in the Hilbert space context. Okay. So I think I also mentioned, yes, so this is one of the lemmas along the way as an independent result in probability convergence for the trace. Okay, now what I'm going to do is pause here and take questions, and then I'm going to move to the second part of the talk, which is in Beamer instead of PowerPoint. The research was in 2 phases, and I learned about Beamer in the middle of that research. I think the other point to make is that, let's see, let me not talk before I find the full screen thing. Should be a full screen. There we go. So I accepted to come to this workshop a year ago and thought it would be great, and didn't know what to talk about because most of my work has not been on high-dimensional regression, except this one piece of work, but this was only going to be a 30-minute talk, so I said I better do some more work. And so that's what this second part of the last 30 minutes will be about. Let me pause for a second, though, and see if there are any questions about what I've talked about so far. Yes,
Mike, I've got one question, which is somehow this is not quite capturing, I think, if you have increasing dimension of the vector, because that would mean that your reproducing Hilbert kernel would also change with n.
The
In other words, I mean, we know that we have to regularize the covariance matrix itself,
right,
rather than simply
right.
putting in the epsilon. So I would guess that this wouldn't help you in those kinds of cases where the dimension of the the observations themselves is increasing.
I mean, the observation, the Hilbert space is still staying the same. The span of the data inside the Hilbert space is effectively growing.
Well, yeah, but your kernel is changing, right? Because
No, the kernel is not changing. The Hilbert space, the embedding Hilbert space is not changing.
no, it's the norm squared of the difference of the 2 vectors, and that norm is a different thing if you're working on in RD or RD plus 1.
So I'm not understanding the point. Are you questioning the theorem, or are you questioning
No, I'm
the
not questioning
application
the theorem
of?
at all. I'm not questioning the theorem at all. I guess what I somehow have a feeling is that the theorem isn't quite, but I maybe totally wrong about this. It's just because coming from the other side, but that somehow not regularizing the covariance matrix itself, I mean, whether you go to a higher space or not, you're not, you will still have some troubles, it would seem to me, if you let the dimension of the vectors themselves. So for example, imagine that the vectors are, you have a sample from the first D elements of an autoregressive process, let's say.
Mm-hmm.
And D increases, right, as you increase the sample size. And we know that in those cases, just using the ordinary covariance matrix will not work.
Mm-hmm.
And so I'm wondering how this.
All right, so fold it up in that. I mean, this. This is we're not making any assumptions about p of y given x per se. So it is being in the empirical process argument, that's being kind of handled. But we have not explicitly analyzed that kind of setting and sort of seen if we could do better by in some sort of a model complexity sort of story. But yeah, that's a good question. So I view this as kind of one of the reasons I want to give the talk here is there's a lot of theoreticians in the audience, and this is sort of our first best step of the theorem on this methodology. But it's certainly weak. Yeah.
What was the suggestion it was?
Third die. Yeah.
I'm just curious. You've got a nice little example there with the wine data with 3 groups.
Yeah.
So you can get a nice 2D picture of it.
Right.
What if you have 4, 5, 10 dimensions, 10 clusters, I think, 10 groups? Are you still hoping to get a nice 2D picture, or how would
Well, so yeah, I guess the right answer here is that we don't have a methodology for picking D. Okay, again, we don't have distribution theory for this methodology, and that's where we need to go. That's where we've been working on that for a while, and we still don't have it yet. So some of the other methods like SIR and others, there is some distribution theory, and there is a data-based method for picking D. But again, I don't think if your assumptions are really wrong, even though if you have a method for picking D, you're not going to necessarily get out very meaningful answers. So I'm not so sure how helpful that literature has been in that sense. But I view a lot of this work as basically for visualization, so for people like you, sort of. So if it doesn't go down to 2 or 3, then you got some other kinds of work to do. I'm not so sure that inferentially I would trust these methods as kind of coming up with the answer, but there's meant to be useful ways of thinking about data. And in fact, this next part of the talk is even more wild in that sense. It's trying to more about visualization. So I would try this for 2 and 3 and see what you learn about data, and then go beyond that. But obviously, eventually, we want to publish this with a true distribution theory and so on.
You have some algorithm. Just stepping back, it has some population version.
Yes.
And you're saying that if in fact there was conditional independence and some chosen for some given some chosen I'm not sure what this D, I'm not sure what the D was.
Yeah,
What
D
you're
is the
putting as
dimensionality of the subspace, this conditional independent subspace.
Okay, so I take it if there is no D-dimensional subspace where you get conditional independence, the population version of this algorithm is doing something.
Yeah.
You're estimating something.
You're estimating
and presumably what you're estimating will then depend on the kernel you choose, since there's no
That's right.
variance. And so what exactly are you estimating?
Another good
And
question.
You don't
yeah.
have conditional independence.
Right, so
What
you
is
have,
the object?
you don't know. So there's some almost conditional independence kind of thing. And you would hopefully that this thing is almost minimizing that, but we don't have that.
Since you don't have conditional independence, how can you describe? I'm just trying to understand what you are minimizing.
No, so we're simply trying to get, to use sort of a characterization theorem to guide us towards an algorithm. And that's sort of the, I think the appropriate thing to do in the face of the current literature. This is a very hard problem. Semi-parametric, find me a subspace. I mean, I think it's as hard a problem as we've heard about in the workshop. And the literature has mainly been assume that there is this such a thing. Here's some procedure I've come up by hook or by crook, and show that it's consistent, and then maybe give some central limit kind of results. And we're simply trying to develop a more classical story. Here's the population criteria, and here's its empirical version, and then we'll show that it's consistent. All right, but the literature has not gone on to the kind of things you're asking about, which is, if you don't have conditional independence, what will you get? And various scenarios in which that happens, and so on.
Mike, could I just follow up on
Yeah.
that? Because I was just curious. There is this notion of Renyi correlation, right?
Yeah. So this is very much.
The question is, how does this, what's the relation between this and Renyi correlation? The Renyi correlation, you you have, you know what, you know, I mean, so it's clearly there must be, because,
Yeah, I think of that as a small, small perturbation away from this. I mean, basically, we started originally with Renyi correlation, and then moved to slightly what we thought was a simpler story, but it kind of is the same idea, that you optimize over some class of functions of a characteristic function like.
right, but I was just thinking that somehow, with Renyi correlation, there's associated an operator.
Yeah.
And somehow there must be an analogous operator somehow.
Yeah, I absolutely believe there is, and it's certainly worth looking at. Yeah, that's a good question. Okay, let me move on, and I have about 20 minutes left, and that's about appropriate, I think, for this part of it. So this is the second phase of this line of research. These are the different collaborators, Fei Shaw and Jens Nielsen. And so the first couple of slides are just reminders of what I've already covered. So slightly different notation using Z instead of U. But there's the sufficient dimension reduction setting. So again, we want to find this conditional independence. So this is just to remind you of the methodology I've proposed so far, this conditional cross-variance operator down here. And here's the theorem which I've already stated. And then finally, this is just a reminder of this algorithm. So the algorithm at the end of the day is to minimize a trace of this empirical version of a cross-covariance operator. Okay, and so as you will hear about later this week by Anne and Partha, and you probably already know, there's a large literature on manifold learning, to which many of you in the audience have contributed. So it's sort of what a differential geometer might want to do is that there's data, and there might, you'd like to uncover in some sense intrinsic geometry underlying a data set. If I have, I don't believe this methodology in many situations. If I have thousands of variables and I believe the manifold is 10-dimensional, I might want to do PCA on 20 dimensions and sort of just drop down to a reasonable dimensionality. This is, I think, is more for visualization and somehow understanding, working with domain experts who may have real manifolds in mind for physical reasons or so on and so forth. So I wouldn't want to overemphasize manifold learning as kind of a discover the truth methodology, but as a visualization methodology is certainly valuable. But we can ask the same questions we've asked before with the linear situation. Often you would have a response variable in mind. You're doing this not just for visualization, but for visualization accompanied by some sort of prediction. So why not try to take into account the response variable? And in Dennis's talk, you certainly, you got a nice historical picture of how the literature went. People for a long time have just done PCA, independent of the response, and found that reasonably well motivated. And I think those of you who are working on the lasso and compressed sensing literature might find that very odd. How would you ever threshold without taking into account the response? It just seems completely ludicrous. Whereas here, it's not as clear it's so ludicrous, and Dennis's talk was basically about saving that also from a modeling point of view. But the same kind of issues come up when you think about the manifold learning situation. If you have a response variable, it seems quite reasonable, even if you're just visualizing, to use it as a guide to to look at the way you look at the manifold. Okay, so we're going to find that there's a very straightforward way to take KDR, which you now hopefully know and love, and combine that with at least one particular version of manifold learning methodology, the graph Laplacian methodology. Okay, so here's the graph Laplacian idea. Basically, let's sample data on some sort of a manifold, and then you take the Laplacian of say the nearest neighbor graph. So I guess I'd assumed that one of the manifold talks would already have happened, but again, take some sort of data sampling on the manifold, find the nearest neighbor graph. So for every data point, find its nearest neighbor. That gives you a matrix. And use some sort of a kernel function, say, for example, the Gaussian. And every time, for every nearest neighbor connection, you evaluate the Gaussian between the distances of the corresponding points. And now form the discrete Laplacian of that matrix. So subtract off the row sums as the diagonal elements, and you get a Laplacian. This methodology, particular methodology, finds the smallest, the eigenvectors associated with the smallest eigenvalues of the Laplacian, and those have been analyzed by a number of people and shown to be approximations to a continuous operator, or eigenvectors of a continuous operator that give you coordinates on the manifold. So here, these first two are the two coordinates that you need to describe the torus. Okay, so we are going to use those eigenvectors in a KDR formulation. So the idea is really straightforward. We're going to compute some number m of the eigenvectors of the normalized graph Laplacian. And then we will define an RKSH, in this case not implicitly with a kernel function, but rather explicitly as simply the span of these eigenvectors. So these eigenvectors have captured some nonlinear intrinsic geometry. They're already an interesting Hilbert space per se. So let's simply use their span to define the Hilbert space for the use of the KDR formalism. Okay? And so now the central subspace we're simply going to, by fiat, approximate as a linear transformation where this V are the, its columns are the, or its rows are the eigenvectors. We simply take a linear transformation phi and we want to estimate phi now. Okay? All right, so we plug this into the KDR formulation. And so if we define phi to be square root of some matrix omega, then this becomes just the gram matrix now written in explicit coordinates that we had before implicitly as a gram matrix, capital K. So it becomes an explicit gram matrix. So again, we minimize this trace, and now we need to eventually back out, we need a square root of this thing if we want to back out these actual coordinates. So we need this thing to be positive semi-definite. And moreover, there's a scaling degree of freedom here. If you let omega go off to infinity, this goes to 0. So let's now get rid of that scaling degree of freedom by making the trace be equal to 1. Okay, so that's our optimization problem now. And again, we know how to solve this basically using some sort of projective gradient on Stiefel manifold kind of technology with incomplete Koleski decomposition and so on and so forth. So here's an example. Let's take the torus, but now let's not treat it as standard manifold learning problem. Let's have a response variable, which is a logistic function of the norm of the two coordinates. Okay, so it's small here, and it grows according to the norm of the two components. So that might be a response variable you'd care to model as a function of these manifold coordinates. So we'd like to discover that from data. So discover a representation of the torus which allows us to predict this y. That's what we're trying to discover. Okay, so this works. So in this particular case, we do our optimization procedure and we get out a matrix omega, and you can numerically discover that its rank is essentially 1. And so they simply write it this way and project onto this vector direction A. So if I do that, and so here's the distance along. I don't have a cell phone, do I? No. Along the direction A, and then this is the response. We've actually uncovered a representation in which y, even though it was a logistic function on the manifold, turned out to be basically linear according to along this representation of the torus. So it's just kind of interesting. So that was in a case where it was noiseless sampling of uniform sampling on the manifold, and then and noiseless y, and we add noise in both cases. We get out this result, and again, it's essentially linear with the added noise. So here's another. Here's kind of one of the reasons we want to do this, which is that we can now define a notion of not just principal eigenvectors, but let's call them predictive eigenvectors. So after you've done the manifold learning procedure, you've got yourself a list of eigenvectors from smallest up to largest. And for visualization in the unsupervised setting, people take the smallest few eigenvectors and then use those as their embedding. We can now scan through the eigenvectors and see which of those has the largest coefficients in the regression. Okay, and so we may pick out the smallest one, the third smallest, the fifth smallest, and so on. All right, and we'll throw away the others. So that's what we've done here. If you keep all of the smallest, in this case, three eigenvectors, here's the representation you get, which is a great representation of the torus per se. I certainly discovered the differential geometry of the torus. But if we want to visualize the response, here's a better representation. Here's the response is by the color code, is going from small to large. So we've now discovered a representation which allows you to predict the response and visualize that representation of the manifold. All right, so here's another instance. This is a real-life instance application of this idea. So we've now taken temperature data from around the globe, 3,000 observation points. That's the y variables. The x's are simply wherever they were sampled on this object, which is a spheroid in R3. And we want to regress the temperature onto x. And obviously we want to do this respecting the fact that this is a spheroid. So again, we found that a one-dimensional representation of this object was appropriate for regression purposes, and so we've plotted that dimension along this axis, and here's the temperature. And again, it turns out that the temperature is essentially a linear function of that nonlinear transformation of the original coordinates. So this is actually the predicted temperature that we get out. This is the central space coordinate, and there's a linear relationship here, and these are our predictions. This is our error in the predictions. And it's really extremely good, except in, I guess, around the Himalayas, in Greenland, and in Antarctica. And I think what's really the situation there is that the temperature ranges are sharp enough, non-smooth enough, that in fact there's where using a representative Kernel-Hilbert space expansion is maybe not appropriate. It's not rough enough to capture those kind of variations in temperature. Okay, so this is the final one, and I'll be finishing. So this is a real large data manifold that we want to visualize. So I think this is a good example of why you'd want to be interested in this kind of methodology for real life. So this is a manifold in 8,000 dimensional space, but it's a 4-dimensional manifold. So we've taken 1,000 grayscale images of 100 by 80 pixels, and there are 4 degrees of freedom. So we've rotated them a little bit, and we've also tilted them a little bit, so tilting is left to right, and done some translations in the image plane. Okay, so rotation, tilt, and 2 degrees of translation. So 4 total degrees of freedom. All right, so we know by construction that there is a 4-dimensional manifold in which these pixels lie in 8,000 dimensional space. We have no idea what that manifold looks like. No one knows. It's quite complicated. So how can we start to visualize that? Well, let's suppose that we're actually so tilt is kind of an uninteresting degree of freedom here. If you tilt, you're going to get a large change in all the pixels. And that's kind of the first thing that any method might kind of come up with is the tilt. Okay, it's giving the most bang for the buck, but it's not as interesting. But whereas rotation is a much more subtle degree of freedom here, and it might be interesting to try to explore that. How does the manifold look with respect to the rotation angle? So this methodology allows you to do that. You treat rotation angle as a response variable, right? And find a representation of the manifold that allows you to predict rotation angle. All right, so we've done that here. So here is this is not the results yet. These are the unsupervised embedded. This is just Laplacian eigenmaps. If you simply take the principal angles and use that as your embedding, it's your kind of usual embedding you get with these methods. And if you then color it by tilt angle, you can see what it's basically done is discovered tilt angle. Okay, and that's like, as I said, if you tilt, all the pixels change a lot, and the method's kind of going to go grab that, which is what it's done. But if you had been interested in rotation angle instead, and you use these principal eigenvectors, here's now a plot with the coloring be that of rotation angle. And you clearly are not seeing anything intrinsic on the manifold that relates to rotation angle. So you have not discovered somehow that aspect of the manifold here. All right, if instead you do the MKDR procedure and you use rotation angle as a response, here's the representation of the manifold you get out, and we now color by the rotation angle. And so indeed you have discovered a representation of the manifold which allows you to predict the rotation angle. So now exploring this thing as a manifold is going to be interesting. So here we are using the predictive eigenvectors. These are not the smallest ranked eigenvectors. These are those that are best predictive of the response. Okay, so I think that's it. Yeah, so this is kind of a vacuous summary. So this methodology putatively discovers manifolds that in some sense preserve predictive power with respect to response variables. And so in some sense it's a gluing together of 2 ideas. It's sufficient dimension reduction now. It's a particular methodology for allowing that to be extended to nonlinear manifolds. And it's allowing the manifold learning people to get interested in response variables. Okay, thank you.
We have a few minutes. Since the audience has already had a crack at it, I'm going to ask a couple of quick questions. In the first part of your talk, you used the EDR subspace. And in the second part, you switched to the central subspace. Those two are quite different objects. And so my question is, are you really pursuing the EDR subspace in the first part of the talk?
No, it really was the central subspace, and the language there was imprecise. Yeah.
The second question is, you were optimizing over Stiefel instead of Grassmann manifolds.
Yeah.
And if the objective function really does depend on the subspace, then there can be infinitely many points in the steeple manifold that will give you the same value of the objective function. Do you have computational routines to get around that issue?
The reason we went to Stiefel instead of Grassmann is we want to be able to work with matrix representations. All of our numerical know-how is with respect to matrix representations. And so it's just a numerical issue. Basically, we know how to, follow paths on Stiefel manifolds efficiently.
And you don't have to worry about flat spots on steeple manifold.
Well, I mean, it's part of the numerical optimization to sort of how to get through them. We follow, we have fast methods for sort of, following geodesics on this manifold. But absolutely, in some sense, the Grassmann is the right manifold to think about it from a theoretical point of view. One point to one parameter and so on. But numerically, it's the Stiefel is better to work with.
Are there other questions?
Yes.
On the example you had on the sphere, the temperature, I mean, the eigenfunctions on the sphere are just the spherical harmonics. I mean, where's the benefit, or what?
Again, we're not trying to find the eigenfunctions just of the sphere. We're trying to find predictive eigenfunctions, right?
By rotation of the basic ones.
By picking of the basic ones, right? By picking of the, so in this particular case, we would, after our procedure runs, we're going to have now a regression on those eigenfunctions, and we can pick out the most highly predictive eigenfunctions. Right? So that's the game. All right? And of course, it's not really a sphere; it's a spheroid, and so those aren't really the spherical harmonics and so on. I mean, the point is that's a method. That's a situation where we kind of know what the answer we expect to get out is, and the fact that it doesn't take the bottom few eigenvectors but finds latitude shows the method is working. Thank you.